So, good evening, everyone. Uh, today, uh, today is the lecture 7 of our TA session for Introduction to Commutative Algebra and Algebraic Geometry. So, in this week also, like in week 7, Professor uh, Dilip Patil, he discussed about this extension of prime ideals and reduction of prime ideals and universal properties of universal map of this localization of a module and and these kind of things. So in the previous week also we did some problems on this localization of modules. We did some Atia McDonald solutions, and today we will be doing some solutions too. Now, since we already know about what is if A is a ring, and again a ring is a commutative ring with unity, so we already know about spec A. So we'll be doing these things only. Now there is a very interesting application about this topological space, which is spectrum of A. And now we'll be doing this problem starting with let phi A to B be a ring homomorphism. Let x equals to spec A and y equals to spec B. If Q belongs to Y, that is, it is a prime ideal in B, then we know phi inverse Q is a prime ideal in A, right? That is, a point of X, right? Hence, phi induces mapping phi star Y to X, right? So what I'm trying to say is that by Q going to phi inverse Q, and you know that this is the contraction that QC. So we'll be doing our first problem today, that is, if F belongs to A, then phi star inverse xf equals to y of phi f. Okay, I will be explaining what is xf and y phi f. Let me finish the proposition first. And hence that phi star is continuous. So what I'm trying to say is that now see that xf is the set of all prime ideals in spec A such that f doesn't belongs to P. Now if you remember correctly what is VF, VF is the set of prime ideals spec A such that f belongs to P. So turns out that, and it is quite trivial to observe, that is VF complement, and we know that these VFs are closed sets in VF are closed in spec A. So XF is open in X. Small exercise, XF F belongs to A are the basic open sets of Zariski topology. Now if I just simply color it with other color, which is should be yellow. Yeah, so this is a remark, and I should put a bracket. Okay, so what I'm trying to say is that you are saying that the inverse image of basic open sets are open. So inverse image of every open set is open, right? Because any open set is the union of basic open sets. So when you take the inverse image of arbitrary open set, so it should be union of inverse image of basic open sets. So union of open sets, so which is open. So yeah, we should do the proof of this one. So proof is quite small and trivial. Okay, so we have following equivalences. That is, Q belongs to phi star inverse XF. This should be equivalent to phi inverse Q to XF. That means that phi star Q is your phi inverse Q, right? Yeah, that means phi inverse Q should be in XF. Yeah, now this means that your F doesn't belongs to phi star of Q, right? A, this means that this is equivalent to saying phi inverse of Q. And if you notice closely, it means that Q belongs to Y of phi F. So the question was that if F belongs to A, then phi star inverse of XF equals to Y phi F. So we have successfully shown that if you start with an element from this, you are getting an element from this, and it is also a reversible map also. So our first proposition is done. Now coming to the second problem, that is if A is an ideal of A, then phi star inverse V of A should be V of A extension. So this is a quite interesting one, that is you are seeing that inverse image of a closed set is also closed. Here your X is spec A, Y is spec B, so there is a map from Y to X via this. So you are seeing that if you take a closed set, that is V of A, and if you take its inverse, it should be V of A. Now again we will have an equivalence relation. Going to next page, we will start from here. Proof. We have an equivalence diagram, that is Q of phi star inverse of VA. This means that Q star phi star Q should be in star Q is in VA, and that means phi star Q should contain A, that means Q should contain A of E, right? Because phi star Q means what? Phi inverse of Q, and phi of phi inverse of Q contains phi of A, and phi of A is contained in Q, so Q contains A extension, and this means that Q belongs to V of phi of A extension. So we have phi star inverse V of A should be equal to V of A. So done. So this will follow some rigorous question set up to 7 problems, but each of them are interesting, and these are very essential and basic in affine algebraic geometry. So what I'm doing is affine algebraic geometry only. So for C, uh, if B is an ideal of, if B is an ideal of B, then phi upper star V of B equals to V of BC. So again, what you are seeing is that if you take a closed set and if you then you observe that the image, the closure of its image is a closed set, and later you will be taking its generalization as uh, the closed image of a map that is of this form. That means whenever someone says that image is a scheme or image is a variety or image is a algebraic set, they mean this closure. And also there is a idea is it's called about the reduced image. That is, you already know that the radical is the intersection of all the prime ideals containing an ideal. So taking the closed set, I mean taking the V set of that radical ideal does not lose anything, but what it turns out is that the coordinate ring becomes reduced. That means it has no nilpotent element as such. So that is how we get this reduced subscheme or reduced image thing. So yeah, we should but I can give this as an exercise, because if you just go linearly as previous one, then you will see that this is also linear as this previous proof. Okay, so we'll be doing the next problem, that is if phi is surjective, then phi star is a homeomorphism of y onto the closed subset V of car phi of x. That what I was just trying to say is that in particular spec of A and spec of A by A, where R is the nil radical of A, are homeomorphic. So homeomorphic So so what you notice is that if phi is surjective, if you are given a surjective ring homomorphism, then you know that the image of a prime ideal is prime, right? So but the other thing is that the if you are given two prime ideals and if you take their pullbacks, they should be same. Now that comes from well definedness also, but anyway, if phi is a surjective, then phi star is a homeomorphism of y onto the closed subset v car phi of x. So okay, we'll be doing this proof. Okay, I'll give you 5 minutes, then we'll start doing this proof. So yeah, we'll be doing its proof. Now, one thing you can notice is that, right? So given phi a to b is surjective, so this implies that phi bar a to car phi is an isomorphism. So we have phi upper star so we have like phi bar upper star spec of b to spec of a by car phi, right? So this is an isomorphism. Now a to a by car phi implies I star of, how should I say this? So has the property that there is an 1-1 correspondence between the prime ideals of A containing car phi and prime ideals of A by car phi. This is true for all ideals, but since we need only prime ideals, so I just wrote it this way. So spec of A by car phi is isomorphic to V of car phi, which is a subset of spec A. So thus phi star of y equals to V of car phi, and that is bijective. We know that phi star is continuous from the proposition A. So all we need to show is that we need only to show phi star inverse is continuous, right? That is the definition of homeomorphism, is right? And you need to notice that phi star inverse is defined from spec B to its image of, so we had that, oh sorry, should be v of car phi to spec b. So this actually restriction map. So what will be, so we need to show equivalently okay, just leave it and I will just do it now. Let y prime equals to v of b be any closed subset of y, and let a equals to phi inverse of b. So your b was from y, so y prime is a closed set in spec b. Now a is its previous image, then we have a following equivalence relation, then we have the following p belongs to phi star y prime, I mean you are just taking its inverse image, that should be phi star of v of b, and should be p equals to phi star of q, which obviously contains b, and this is equivalent to, as you can see, p equals to phi inverse of q. Again this contains bc, and this is equivalent to p belongs to v of bc. So this implies that phi star of y prime equals to v of bc, and in particular that phi star of y prime is closed when y prime is, and therefore that phi upper star is a homeomorphism. Now you can just take a natural surjective projection map from, now for the second part take the natural surjection map from A to A by R, then you can see that this is a homomorphism. Okay, so now we'll be doing another interesting problem, that is problem 5. If phi is injective, then phi upper y is dense in X. You know what is dense set? That means if you take its closure, then it will be the whole set. That is phi upper y closure equals to X. More precisely, phi upper y is dense in X. This is equivalent to car of phi belongs to the nil radical. This is relatively easier of what we have learned till now. So it's take 5 minutes. We'll be doing this from 6:45. Okay, so I was thinking about how to do this using previous solution. Okay, uh, maybe we can go through like this. By the previous statement, we have phi upper star y cover phi upper star v of 0, right? Because y is the whole set is the, I mean 0 ideal is contained in every prime ideal. So yeah, now this is coming from 0c, right? From one of our previous assignments, yeah, like 3, question number 3, if you go there. Yeah, this is, if you take v as 0, then v of 0c, and which is kernel, right? The previous image of 0 is kernel. So, and you know that v of car phi should be uh, yeah, I mean, yeah, so thus phi upper star of y is dense in X. This is equivalent to saying phi upper star of y bar equals to v of car phi equals to X. That means what? That means car phi belongs to P for all prime ideals P. This means that car phi belongs to your nil radical, right? So we are done. Now if phi is injective, then we know that this car phi should be 0, right? So then your 0 should be in the nil radical, because 0 is itself a nilpotent element. So we are done. So there is another problem, but we should move on to other directions. Now we should be doing some problem. See, okay, we should be doing this radical thing more, what I just used, so should be interesting. Problem number 2. So this is done, so I'll just wrap it up here. So problem number 2. No, do it. Okay, we should be doing this. So it consists of the ideas of uh, multiplicatively closed set, the contraction and extension of prime ideals, and all those things. So I think it will be a good problem for all of us to try. A multiplicatively closed subset is offering A is said to be saturated if xy belongs to S, equivalently x belongs to S and y belongs to S. Prove that one, S is saturated if and only if minus S is a union of prime ideals. Okay, this is completely stepping up to another type of problem. So just take some time and think and let me know, or else you will be doing this in 5 minutes. So we'll be doing this theorem, that is, we shall prove that if AC is saturated, then A minus S should be union of all the prime ideals such that its intersection with the saturated set is empty. Indeed. Now it's obvious that the left hand side contains the right hand side, right? Because if you take any element from here, suppose small p from capital P, and that is not in small s, then it is capital S, so it is not it is in the A minus S. Yeah, this containment is fine. Right hand side here. Now for the other direction, let small x belongs to A minus S and let the ideal generated from this is called A. Then if we let S by A is the set of all the left cosets of the abelian group, be the set of cosets of S in A, we observe that 0 closure equals to 0 plus A does not belongs to S plus A, because that would imply S intersection A is non-empty. Which is absurd by the saturation condition of on S. So all I'm trying to say is that 0 doesn't belongs to A, because if 0 belongs to S by A, that would imply that A belongs to S, or at least that would imply that S intersection A is non-empty. But we have taken x from A minus S, and if A belongs to S, or at least has an element, then it should be that x dot y should be in S. That means x should be in S, but that is not possible. So yeah, also S by A is multiplicatively closed as a subset of A by A, because this is trivial, right? Because S is, image of a multiplicative closed set is a multiplicative closed. So if you just take the quotient map A from A by small a, then you would see this. So we have done this in last class, exercise 6 chapter 3, Atia MacDonald. There exists a maximal multiplicatively closed set A minus P closure, where P closure, that means P bar, is a minimal prime ideal such that is this minimal prime ideal must be of the form P by A, where P is some prime ideal that contains A. In particular, P intersection S should be empty, and this shows that X belongs to the right hand side. Thus, the other inclusion A minus S section is MTP holds, and we are done. Now following this, we can do this problem also. Yeah, if S is any multiplicatively closed subset of A, there is a unique smallest saturated multiplicatively closed subset S bar containing S and that S bar is the complement in A of the union of the prime ideals which do not meet S. We call S bar as the saturation of S, and following this we can show that if S equals to 1 by A, 1 plus A, where A is an ideal, find S bar. So try this for 5 to 10 minutes, then we'll be doing this. Okay, so now should be doing this on a proof. If S is multiplicatively closed, then S bar is a set that contains S. Now, if bar were any saturated and multiplicatively closed set of S bar that contained S, then its complement in A would contain at least one prime ideal that has non-trivial intersection with S. But then this intersection would belong to both S and to A minus prime closure A minus S, which is a contradiction. So S is minimal. Now to the last question. If we put one by m, we immediately see that if and only if plus a equals to 1. Therefore, intersection 1 plus a should be empty if and only if there is some prime ideal p prime such that p prime containing p plus a, but then you can see that one this prime a minus so we are done. So now we'll be doing this problem. This is problem number 3. Let ST be multiplicatively closed subsets of A such that S is contained in T. Now let phi S inverse A to T inverse A be the homomorphism which maps A by S, S inverse A to A by S considered as an element of T inverse A, so that TFA the following are equivalents. 1. Phi is bijective. 2. For each small t of t by 1 is a unit in S inverse A. For each small t of capital T, there exists x belongs to A such that xt belongs to x. For T is contained in the saturation of S, and the fifth one is every prime ideal which meets T also minutes. Yes. So yeah. uh, okay, take 5 minutes, then we'll be starting this proof because it will take some time. I'll be doing this little faster, so you can just pause the video and take your time to think. Uh, So yeah, we should start doing the proof, and this will be our last theorem today. Okay, so we have the following. From 1 to 2. In particular, phi is surjective, and this implies that t by 1. Okay, when you are seeing this lecture, it would be better if you just have a copy of my notebook which is uploaded in the drive, and you see this you see the question beside you, so that when I am explaining this can be better understood. Okay, this implies that t by 1 of t inverse a can be represented as a by s for some a of a and s of s. Now if a by s, a belongs to s, then a by s equals to t by 1 is invertible in s inverse a. Otherwise it's the relation st minus a u equals to 0 for some u belongs to s, that implies invertibility of t by 1. Now for 2 to 3, if the inverse of t by 1 is x by y, then there is u belongs to s such that ux of t equals to yu as desired. Now for 3 to 4, it's obvious that no element of t could belong to a prime ideal that meets S. Therefore, T is contained in P intersection S empty P is closure. So yeah, so you are seeing that all those steps are quite easy except for the last one, and this is also trivial because you can see that if T is contained in the saturation of S, then from the previous corollary what we have done, that you can see that every prime ideal which meets T also meets S. Now for the last part, we will show that phi p bar is inverse A p bar to T inverse A p bar is bijective for all prime ideals p bar of S inverse A. So this will imply that the phi itself is bijective, because bijection is a local property, right? Because injection and both surjection both are local property. Then it's a standard theorem in Atia MacDonald from proposition 3.9. Atia MacDonald, we see that phi is bijective. Now note that any such ideal must be of the form S inverse P, because you know all the extended prime ideals look like this, even all the extended ideals look like this, where P is a prime ideal of A that does not meet S. By 4, this condition says P intersection T is empty too. Indeed, an element of S inverse A, S inverse P has the form A by S1 by F by S2, where A belongs to A, F belongs to A minus P, and S1 S2 is right. If phi of S inverse P equals to A by S1 by F by S2 equals to 0, then there would be star S3 belongs to S inverse P such that F dash S3 A by S1 be F dash A S3 by S1 equals to 0. This in turn implies that there exists small t of t such that t of a in A, but then tf dash does not belongs to P, since f dash does not belongs to P and T intersection P is empty. Thus tf dash by 1 does not belongs to A. Hence A by S1 F by S2 equals to 2 dash A by S1 and Tf dash F by S2 is to 0. And so phi inverse P is injective as desired. In order to show surjectivity, note that an element of T inverse A S inverse P is of the form A by T F by S, where A belongs to A and S belongs to S and F belongs to A minus P and T belongs to T. Since T belongs to P, we have 1 by T by 1 belongs to T inverse of A S inverse P. Thus A by T by F by S equals to phi of S inverse P Ta by 1 Tf by S and phi S inverse P is surjective, and we are done. So these problems are great in terms of revising your theorems and whatever you have learned till now, because the course structure has been designed in terms of fast learners and who who are getting introduced to these topics only. But while the theorems are quite simple to see and understand, but when you do some problems, there it becomes non-trivial, because so many topics and so many definitions are there. To use them precisely where we need actually little trickier. Okay, so we'll be meeting on next Tuesday. So okay, keep working hard. Good night.